which Esperanza and Miguel are initiating here in Yunnan, and how we can see rapid environmental changes on decadal, centennial, and millennial timescales in paleo studies. And that's what I propose to try to talk about today. First of all, gamma ray spectrometry. We have a range of different gamma ray detectors which can be mounted on mobile platforms. Airborne gamma ray spectrometry puts large radiation detectors onto low-flying aircraft, and is probably the largest area coverage that you can achieve in any mobile form of gamma radiation spectrometry. The gamma rays from the Earth's surface convey information about natural radioactivity in rocks and soils, and gamma rays from anthropogenic nuclides, the radiocesiums, nuclear accident fallouts, tell us about surface environmental processes. We can also today increasingly geocode mobile spectrometry, which can be carried on people's backs or put onto special vehicles to capture data with spatial resolutions, say 10 to 100 meters. Those are the gamma ray spectrometry approaches. There are a range of different detector types which can be used for this type of surveying. The main two technologies remain the high resolution, cryogenically cooled semiconductor detectors, which have really good energy resolution, but low sensitivity, and also they are quite fragile. And then there are low sensitivity, low resolution spectrometers, which have very high volumes. The type of system we put in a helicopter would be a detector weighing 100 kilograms, which can make a measurement in 1 or 2 seconds. There are some examples here of the type of spectra that we would get. This example is from a helicopter survey in Belgium, taken over the top of a radiochemical separation facility. And the low resolution spectrum shows the naturally occurring thorium, uranium, and potassium signals. But the high resolution detector, which has far fewer counts, also shows the resolved peaks from iodine 131 and molybdenum 99, which are being used coming from the production of radiopharmaceutical chemicals. So we can see more detail. This spectrum is a low resolution spectrum taken in Japan after the Fukushima nuclear accident, and we can see the natural peaks, but we can also see the isotopes of cesium, the 30-year half-life cesium-137, which is a fission product from the nuclear reactor, and the activation product cesium-134. Here we see the high-resolution equivalent. So there are choices with detectors depending on whether the type of nuclear spectroscopy is more important than the speed and area coverage. I want to show you some old data recorded in the UK after the 1986 Chernobyl nuclear accident. The reactor accident took place on the 28th of April 1986, and for approximately 10 days, the nuclear reactor was on fire, releasing radionuclides to the atmosphere. In Scotland, we had rain clouds arriving in the first days of May, which carried radionuclides all the way from Ukraine to Northern Europe. And we experienced contamination of a number of environments where it rained heavily. This is a paper published in Nature based on rainfall monitoring of the areas believed to have the highest deposition. And we imposed restrictions on agriculture in West Cumbria and North Wales and parts of Scotland because of the transfer of radioactive cesium to the upland grazing place where sheep graze. In the 1 or 2 years afterwards, I conducted an airborne gamma ray spectrometry survey for our Ministry of Agriculture over 45 square kilometers with a helicopter, and we registered radiocesium distributions on the mountaintops up to 40,000 becquerels per square meter. Now, what I'm going to be talking about here is a later study which was conducted to to try to see whether we could extract information about the spatial reproducibility of this technique and also its ability to measure change. When we're collecting data, so we have two main questions here. If we increase the survey line spacing, to what extent do we lose quality of information? And how would we quantify change over time? Now, when we're collecting data using these techniques, the aircraft is flying down certain pathways, recording a time series of spectra which are labeled with position. But if we have more than one survey, we won't have observations on precisely the same locations to make a point of comparison. So the first process in trying to make these comparisons is to regularize the data set onto the equivalent of a regular grid. And this is done by a nonlinear spatial weighting algorithm. We also have estimated uncertainties of the observations, which can be propagated for each of the positions for which we wish to re-estimate the quantity. And once we have regridded and regularized the survey data set, we can measure the difference between different surveys using time series manipulations of these data sets. So let me show you an example. So this is the area I showed you before, resurveyed in about 12 years after the original survey. We record gamma ray dose rates and the cesium-137 distribution across the same area I showed you before. We did a study in this of what would happen if instead of having 500-meter line spacing, we had 1 kilometer line spacing, 2.5 kilometer line spacing, or 5 kilometer line spacing. And this was achieved by resampling the data sets and reanalyzing them. And the statistics show that our estimate of total activity is surprisingly robust to dropping data out. This is in the upland area that I've shown you. And in a, Then if we take the two data sets which are separated by 12 years, the original one and the first one, and we perform the regridding and time analysis. I'd like to show you the results here. If we added up all the activity within the first survey, we came to a total estimated cesium concentration of 9.35 terabecquerels. That's 10 to the 12 becquerels. The radionuclide has a 30-year half-life, so if we decay correct that level to what we should have in 2000, we come to 7 terabecquerels. And if we take the later survey and we estimate from it, we end up with 7.22, which is in remarkably good agreement, within 3%. But when we start comparing areas which are on the tops of the fells, Corney Fell, Black Combe, and Loweswater Fell, and we look at what's happened in the meantime, we discover that there has been a reduction in the amount of radioactivity sitting on top of the mountains. And when we look at the low-lying land, we discover that there has been an increase. What has happened, these are the mountain tops, is that the radionuclides have migrated down slope. Blue on this picture represents a loss of activity, and the orange and red colors represent an increase. So we're seeing in this spatial visualization based on high sensitivity, airborne gamma ray spectrometry, we're able to trace the movements of the materials containing the radionuclides in a landscape on decadal timescales. We have another area which is on the coastline to the north of the one I've shown you, where sediments which have been contaminated with radiocesium from discharges from the Sellafield nuclear reprocessing site are washing the coastal zones in the tide-washed pastures with radionuclides. So radiocesium here follows the deposition of tidal redeposition of sediments from the coastal zone. Once again, in this area where we have 50-meter surveys, we've looked at the reproducibility by taking the 50-meter data set apart to two 100-meter data set subsets, 5 250-meter subsets, and 10 500-meter permutations. And when these are reconstructed, total activity is also well reproduced. I have a number of surveys of this area to compare for the time change. We have a survey in 1999, one in 2000, separated by 1 year. And we have a survey in 2009 from a smaller study. What we discover, even on the 1 year timescale, is that there has been a change in this salt marsh and this edge, where there is an erosional process which is taking sediments which are less radioactive than the ones that are underneath and re-exposing them. And there's a depositional process where sediments from the tidal area, which have a lower concentration of radionuclides than those on underneath, are being actively deposited. And we can see these environmental changes, which correspond to physical processes, very clearly by the time series analyses of these spectra. So that is trying to show you that these airborne techniques aren't just for spatial visualization, they can be quantified and they can produce useful traces of process change. We can use the same algorithms to compare data from different teams, and some years afterwards, in the early 2000s, we hosted an international validation exercise to try to bring the European teams who did this sort of work together. This is published. I now want to hop from the UK towards Japan after the nuclear accident in 2011. We have these small geocoded backpacks, which can record the data, produce a moving map, a real-time analysis when you walk around the landscape. And here is a survey of the University of Fukushima conducted in the, let's say, at the end of the first year following the nuclear accident. We have a certain amount of area that has had soil removal, and we can quantify the levels of reduction in the radionuclides caused by active remediation. We did quite a lot of work with Japanese teams to take soil samples, to embed these techniques into their environmental monitoring, to create calibration sites on flat grassland, in this case in a fruit tree research center, in this case on the campus of the university, where other people would calibrate their detectors. And the samples were split and analyzed partly in the UK, partly in Japan, to produce a cross-validation, which worked out extremely well. I'd like to draw your attention to the vertical profiles of activity versus depth in both of these sites. So we have in becquerels per kilogram on the top surfaces, maybe 10,000 becquerels per kilogram in the top centimeter or two of activity. And when we go down 5 to maybe 8 grams per square centimeter, the activity level has declined by 3 orders of magnitude. But there is a small component of radiocesium, and it is in both the 30-year half-life and the 2-year half-life, which has very rapidly gone to greater depths. That has migrated vertically faster than the main exponential component. And that's another example of measurements of rapid change. Within the first year of the accident, some activity had reached the rooting zones of plants. Another study here in a forest, which was conducted with support from the UK government as part of a project looking at the potential for synergistic biomass energy harvesting and phytoremediation of contaminated forests. Can we trim the trees, remove forest litter, generate biomass electricity, but remove the radioactivity from the site at the same time? Fortunately, that was not my job, but we conducted radiometric surveys before and after a community project to remove the forest litter to see how much it cleaned the forest up. And this is a small area that was cleaned up. By doing surveys twice, once in 2013 and once in 2014, we were able to measure the environmental change in the amount of radiocesium before and after this remediation activity. Now, this area shows the reduction, which was caused by active remediation, but when we look at the area that was not remediated, we discover that self-remediation was taking place by downslope movement of the radionuclides. So we have areas here where there's been a loss of radioactivity over the year by a natural process, and there are other areas where there's been an increase as a result of the migration of the radionuclides. So these are another example of the same technique for spatial regridding and measurement of change, producing visualization of the short-term movement of radionuclides on a spatial scale. I'm going to show you a helicopter survey as well, which we did by preparing some of our spectrometers in the UK and flying them together with the Japanese Atomic Energy Agency near the Fukushima site. Here is the Fukushima site with the damaged reactors here, there, and there, and also storage tanks which have had contaminated water stored on site from the groundwater, which is constantly going through these damaged reactors. There we go. So we flew 3 spectrometers in a number of areas to the north and to the south of the reactor site. The major releases that deposited radioactivity on land were projected into the northwesterly direction, but there's a small side plume that went out to the southwest. And I'd just like to show you the registration of this cesium-137 in 3 different spectrometers. The activities, I'm sorry, the scale is not so easy to read, but it goes up to several hundred kilobecquerels per square meter. And when we place these onto digital terrain models, this is the area north of the site and this is the area south. I don't know if you can see that we have extremely good registration of the location of the activity relative to steep valley systems. And this provides some indication where we might expect the migration and the runoff paths to take place in the future. On this area, the southwesterly one, we can see that the radioactive cloud came out in this direction. On the first mountain, we have deposition both on the rising and falling edges, and on the second mountain range, only in the rising edge. Now, that is interesting because it tells us that there was deposition from dry deposition on the back slope of the mountains, but wet deposition on the front slope. And we can also see in these visualizations where we see the potential for transfer down valley systems. And that's all I wanted to say about radiometrics. My question was, can we spatialize and quantify environmental change over annual to decadal timescales? And I would hope that the answer is self-evidently yes, of course we can. By radiometric mapping airborne vehicle or backpack, we can not only show changes, but we can show that it corresponds closely with spatial boundaries and physical environmental pathways in a meaningful way. The quantitative images show a high level of coherence, and time series analysis shows colluviation, erosion, and redeposition, which can be visualized and quantified. So if we think about the future and the challenges, I put it that we should be able to use these techniques if we have the inclination to reveal changing rates of environmental processes as we enter the Anthropocene. Okay, so that's one part of what I wanted to suggest, since I am reaching the end of my research career, to suggest what other people might wish to do in the future. And now the second part of what I want to talk about is luminescence.